So you remember one of my original slides, it had characteristic actions on the one side and it had resistance on the other side. So we're going to look for a while at characteristic actions, and then we will look at EN 1990, which brings together characteristic actions and the resistance. So characteristic actions then, generally a 1 in 50-year event. So these actions are not going to happen very commonly. Lots and lots of options for national determination. So you in the Ukraine, you know about your snow loads, you know about your wind loads, you know about temperatures. And that's why it's important that you would look in the national annex. So these are the parts that we're going to look briefly at, although I'm not going to cover 1991, 1, 2. I'm not considering fire today. So 1991, 1 is an important standard because that will tell you about imposed loads. It will tell you about imposed loads on floors, and it will tell you about imposed loads on roofs. So I would imagine that these sorts of figures are familiar to you from your current design practice. Those figures are from the Eurocode, and as I read your national annex, I think those figures are adopted by the Ukraine national annex. In the UK, I have to say that despite this value of 2.5 kilonewtons per square metre being recommended, most of the design in the UK would be based on 5 kilonewtons per square metre. In fact, as well as the 5 kilonewtons per square metre, we would also allow an allowance for partitions. So normally it's 5 plus an allowance for partitions. I'm concerned about that because really we are over-designing. Perhaps we should think about designing just for 2.5 kilonewtons per square metre. Again, traditionally in the UK, for partitions we would have allowed 1 kilonewton per metre squared. So we have a phrase in the UK which would be 5 plus 1. So designers in the UK talk about 5 plus 1. And what they mean is 5 kilonewtons per square metre imposed load and then 1 kilonewton per metre squared for partitions. The Eurocode is very, very specific for partitions, and the allowance for partitions depends on the weight of the partitions. And I am amused by the Eurocode because this table is for movable partitions, and I cannot possibly imagine that I would be able to move a partition that weighs this much. That's a very heavy partition. Okay, so having determined the load on a floor, the Eurocode says it is unlikely that all of the floor will be exposed to that full load. So if you have a large area, there are reduction factors. The larger the area, the more reduction there is. And again, I looked in the Ukrainian National Annex, and this is one good example where your National Annex changes the Eurocode recommendations. You have very specific rules for the application of this reduction factor. So there is the recommendation in the Eurocode. You have some very specific and slightly different reduction factors, and those are those down at the bottom. And I think you would recognise these because these, I think, are out of your previous national standard. As well as a reduction in the imposed load for a large area, there is also a reduction for the number of stories. So again, this is an issue to do with probability. What is the probability that every single floor in a multi-storey structure will be at that full level of load? It's a reduced probability, so there is a reduction factor. And again, your national annex varies the recommended approach. So I'm trying to throw in one or two examples to demonstrate how important it is to look in the National Annex. Imposed loads on roofs. The National Annex here in the Ukraine, I think, adopts the recommended value. So I think the imposed load on a roof, according to the Ukraine National Annex, is 0.4 kilonewtons per square metre. The 0.4 kilonewtons per square metre is really to represent people and perhaps some maintenance load and perhaps some maintenance equipment. It does not represent snow. So we're going to determine the snow loads from a completely different part of the Eurocode. Okay, 1991-13 covers snow loads. It covers exceptional snow loads, and it covers drifted snow. The core Eurocode map is not very helpful for the Ukraine. So that's a good example of where you will need to refer to the Ukraine National Annex, because the Eurocode, in fact, is not saying anything about snow loads in the UK. This is the example from our National Annex, and you can see that we are very detailed in our National Annex about snow loads in the UK. And maybe it would be slightly different in the Ukraine, maybe perhaps not as detailed because you're far away from the sea. But certainly different countries will have something like this to give them a map of the snow loads. Having determined the snow load, then there are a number of different cases to consider. So the normal cases, if I could describe it that way, would be number one, which is uniform snow across the whole of the roof, and secondly, where the snow has been removed, perhaps blown off one of the roof slopes. So cases 1 and 2 on this slide are described as normal load cases. Those would be the ones that you would normally consider. And then drifted snow, which would be something which happens in a valley. So if the two roof slopes are forming a valley, or maybe behind a parapet. So at the edge of a roof slope, there might be some upstanding parapet here. So snow would accumulate behind the parapet. Or perhaps if you had a low building adjacent to a tall building, snow can blow off the tall building onto the lower building. And those situations are described in the Eurocode as an accidental load case. So there are different rules, which we will see later on when we come to EN 1990, that deal with the normal cases, number 1 and 2 on this slide, or the accidental case. So here are the two additional cases, as well as uniform snow. Then you'll see case 2 at the top there is snow removed from one roof slope, and case 3 is snow removed from the other roof slope. In the UK, it would be unusual to check both of these cases. Perhaps we are being lazy, but generally we would only check the uniform case. In the Eurocode, the design snow load, that's a shape coefficient. Some tricky words to translate here, I think. It's a shape coefficient multiplied by two factors, multiplied by the snow load on the ground. And the recommendation is that these two factors are set to be 1.0. If you do set them to be 1.0, then perhaps that would be familiar to you, that the load is equal to a coefficient to do with the shape multiplied by the snow load on the ground. And Here is the coefficient, and you will see that it's to do with the roof slope. So along the bottom of this figure we've got the roof slope, and on the left hand side we've got the coefficients. So for very many roof slopes the coefficient will be 0.8. I've spoken about snow drifting. This will be a key design case for you to check. So in valleys, behind parapets, behind obstructions. But remember, there are special rules in EN 1990 to deal with accidental actions, which we will see a little bit later on. Now, EN 1991-14 covers wind actions. And in the United Kingdom, we will hate the calculation of wind actions with a deep hatred. There is nothing worse than calculating the wind loads for a structural engineer in the United Kingdom. So we would try very hard to avoid calculating the wind loads. We would tend to use free software that may be a manufacturer of purlins for roofs or a manufacturer of cladding for roofs that they make available. We would much prefer not to use the Eurocode. We would like to use software. Otherwise we will grow old and grey working out the wind loads. So the basic process is that we calculate a peak velocity pressure. There is then a structural factor. There are then lots of coefficients, and then we can calculate wind forces. So this is not a straightforward task, and I would still recommend that you use software. So this is an overview. We would take the basic wind velocity from some figure, and that will be a figure no doubt in the National Annex. We allow for site altitude. We allow for the ground roughness. So if you are in a city or in a built-up area, it will be different to if you are in the country. If you are on a slope of a hill, it will be different. The upwind slope or the downwind slope. If you are far from the sea, it will be different. So all these factors go into the calculation of the wind loads. So I would expect that in the Ukraine you will have something in a national annex which tells you about the basic wind speed. Clearly the core Eurocode is not sufficiently detailed to cover all the countries. Then we would allow for the altitude, we would allow for the type of ground, whether we are in the town or whether we are in the country. We would allow for the distance from the sea. And then there is a size factor, which is to do with if you have a large area, will the wind be at the peak pressure over the whole of a large area? And it will not be. So the larger the area, there is a size factor, which will be a reduction factor. There is a dynamic factor. And then there are coefficients on the roof and on the walls. So I understand that in the Ukraine, your previous practice was a much simpler approach to wind than the Eurocode. This is very, very complicated, I have to say. So then there are questions about what do we do with high local suctions? Do we ignore them? Do we design the whole of the structure for these high local suctions? Or do we spread perhaps this high local load in the surrounding area? Then there is an internal pressure. The coefficients that you see on the screen here, plus 0.2 or minus 0.3, they assume that all the doors and the windows are shut. So even if all the doors and windows are shut, the Eurocode says you either calculate the internal pressure coefficients or you use the two cases, plus 0.2 or minus 0.3. If a door is open, then you need to make a decision. Are you going to carry out the design assuming that the door is open? Because then the internal pressure coefficient will be much greater than plus 0.2 and will be much less than 0.3. So that may well turn out to be a dominant design case. So the phrase that the Eurocode uses is, are there any dominant openings? So a door or a window, or a door to let lorries into the building, for example, if that were open, that would be a dominant opening. Practice in the UK is to assume that all those openings are shut. If we assume that all those openings are shut, and therefore we base our design on plus 0.2 and minus 0.3, then the Eurocode is very clear about what we must do. We must consider the door being open as an accidental situation. So that would be my recommendation to you. I would assume that all the doors and the windows are shut and use the internal pressure coefficients as plus 0.2 or minus 0.3, but then consider the accident of the door being open. And that will be valuable because you can recalculate the wind pressure using a lower probability factor. And that will be helpful because the pressure will reduce. And secondly, because it is an accidental condition, when we look in EN 1990, you will see that the factors, if it's an accidental condition, are much smaller. So if you consider it an accident, that will be a valuable piece of advice. Of course, if you are designing a building and it is an ambulance station or a fire station or something where the doors will be open even if there is an extreme storm, then you should not consider it as an accidental situation. You consider it as an ordinary, normal situation. Okay, we've moved on to a different part now, 1991-17. And 1991-17 covers accidental loading. So it tells us what accidental loading is, snowdrifts, which I've already spoken about. This idea of an opening being a dominant opening, which I've already spoken about. And finally, robustness, or tying rules, or the avoidance of disproportionate collapse. And I just want to say a few words about that topic. So disproportionate collapse is to make sure that if there is some event, and the Eurocode is not clear what that event might be, it's an unspecified event, but if there is an event, the robustness rules are trying to prevent disproportionate collapse. You don't want the result of the event to be disproportionate to the original event. So you want the building to survive. It may be bent. It may need additional work before people can use it again, but you don't want the building to collapse. And this, I think, was the original source of these disproportionate collapse rules. This is quite a well-known structure in the United Kingdom. It's called Ronan Point. It's a multi-storey block of flats. And a lady on the 18th floor left her oven with the gas on and the door of the oven open but not lit. Then there was an explosion. She survived, by the way. There was an explosion. And that blew the walls of her flat off the building. But unfortunately, the walls of the flat were supporting the floor above, so the floor collapsed. And that floor was supporting the walls above, so the walls collapsed. And the collapse went all the way to the top of the building, and then the collapsing debris caused the lower stories to collapse. So remember, on this particular building, the explosion was somewhere near the top, on the 18th floor. And it was decided that the results of that explosion were disproportionate. So since then, there has been, certainly in the UK, and now you find this in the Eurocode, there has been rules to make sure that beams are tied into columns, for example, to make sure that if there was some event, like an explosion, that the column cannot separate from the beam. It is very likely that the connection will be deformed. It is very likely that the column will move, but the objective is to make sure that the column is still in position and still supporting the floors above. So the Eurocode then, first of all, talks about how you provide robustness. It gives options to perhaps prevent the event in the first place. So in the United Kingdom, you will know that some years ago there was quite a lot of terrorist activity in the United Kingdom. So maybe we would put concrete walls to stop cars getting close to buildings, for example. The Eurocode says that you can design for the action, but usually the forces that you are dealing with are so large that to design for the action will be very difficult. The forces that you need to design for, or the robustness that you need to provide, depends on the class of building. So in the Eurocode you can see that there are 3 classes, although class 2 is split into class 2A and 2B. That is the core Eurocode. The Ukraine National Annex is much, much more detailed than the core Eurocode. So if you are concerned about robustness, you must look in the Ukraine National Annex, because the classification of a building in the Ukraine National Annex is much more detailed than the Eurocode itself. In the Eurocode, these are examples of class 1 structures. So the consequence of collapse for a class 1 structure is perhaps not very significant. It's only a house, or it's only an agricultural building. So those are the rules which describe a class 1 structure. These are examples of class 2 structures, so the consequence of collapse is rather more significant. So hotels, offices, industrial buildings, and places where the public go. But for example, this class, where the public go, but limited to 2 stories, so a relatively modest structure. And those are the descriptive rules for class 2A. This is class 2B, so much more significant structures now. Multi-storey buildings. Car parks, I'm not sure why car parks are class 2B. And hospitals. So one can imagine that the results of a collapse in a hospital would be unacceptable. And those are the descriptions of class 2B. And if any structure is more serious than a class 2B, then it will fall into a class 3. So very tall multi-storey offices, public places on the left here where lots of people go, or on the right, hazardous processes. And the classification for class 3 is anything where the repercussions or the results are more serious than class 2B. So these are the things that 1991-17 tells us. It tells us about horizontal tying, so that would be tying beams into columns. So for example, as well as sustaining a vertical shear load, we would be ensuring that the connection can resist a tension in the beam. So that would be horizontal tying. Vertical tying is because we will tend to splice the steel sections, larger sections at the bottom, smaller sections as you go up the building. They will be joined together. And the assumption is that one of the columns at a lower level will be removed, and therefore the column, instead of working in compression, is working in tension. So for most splicers, the robustness rules, that tension force, that will be the dominant design case. And we'll talk about that a little bit later on. You should note that to check a connection for this tying force, let's imagine a beam and a column, it's an independent check to verifying the connection for the vertical load. Check the connection for the vertical load, and then as an entirely independent check, you check it for the axial tension. It's clear that those are independent checks because when we verify a connection for the vertical load, then perhaps we will be using the yield strength. We are carrying out an elastic check. When we check the connection for the tying force, we will be using the ultimate strength. You cannot combine yield strength and ultimate strength at the same time. They are independent checks. Because we are using the ultimate strength, of course, that's why we expect some permanent deformation to take place. Before we reach ultimate, there will be a lot of movement. So here are the rules then. In Class 1 building, you remember that was perhaps a house or perhaps an industrial or perhaps an agricultural structure. The Eurocode, we don't have to worry about it. Class 2A, we need to provide horizontal ties, and there are some rules here about the tying force. If you are not familiar with the Eurocodes, I will go into this in more detail later on, but G would be the permanent action. So if it's a G, it's always the permanent action. If it's a Q, it will be the variable action. And I will talk about this Greek symbol, which I call psi, later on. But that will be the formula that you will use to calculate the horizontal tying force at those connections. So here is a typical numerical example. I have assumed that the permanent action is 3.5 kilonewtons per square metre. So in my world, that would be the typical composite floor. I've assumed that the variable floor load is 5 kilonewtons per square metre. And for the enclosed floor load, the value of psi is 0.5. I've assumed that my beams are at 3 metre centres, because that would be typical for composite construction. And I have assumed that the beam has a span of 6 metres. So my tying force is 86 kilonewtons. So I would need to verify the connection for 86 kilonewtons. Notice that the vertical shear, 128 kilonewtons, so I hope that gives you a reasonable idea that the tying force is a little bit less than the vertical shear force. Okay, so for horizontal tying, that means our connections have to resist the vertical load and perhaps an axial tension in the beam. And I've said this before, so this is just a reminder, we are expecting the connection to buckle. It will not be perfect. It will be bent. All we're trying to do is to make sure that we are holding the beam to the column. It does not blow off. So there is a challenge then to connection designers, because in my world, in the UK, 99% of my connections would be nominally pinned connections. So I would be designing the beam to assume that the beam is simply supported, carrying no moment at the end connection. I can design the connection to carry the vertical shear, no problem. To make sure it is nominally pinned, perhaps my end plates might be 8 millimeters thick, or maybe 10 millimeters thick. That would be a very standard connection detail for me. But I also have to design the connection to resist a tying force. That will be a problem if the end plate is only 8 millimeters thick. So perhaps I need to put a 12 millimeter thick end plate on, or maybe a 15 millimeter end plate on. And maybe it is 15 millimeters and then welded to the top flange and the bottom flange. But if you weld a 15 millimeter end plate to the top flange and the bottom flange, I do not think that it is nominally pinned. So I think you will be carrying some bending moment into the column. Vertical tying then will have an impact on the design of your splicers. So you will need to verify your splice, imagining that the whole load from one floor is carried in tension on the splice. So these would be ordinary splice details in the UK. The one on the left would be the most common detail, and I would know this as a bearing splice. So in compression, the load is being carried directly between the flanges here. The bolts and the plates here are not designed to carry the compression. They are just to give the splice some stiffness, that's all. Just stiffness. So that does mean that for this detail, if we had to design that for a tension, then the bolts and the plates would need to carry the tension force, and that would be the dominant design check. In compression, no problem. In tension, we would need to check the bolts and the plate. Now, ladies and gentlemen, when you see a yellow star which has just appeared, it means that I have changed the slide that you are about to see. So since I prepared these slides, and since they were translated, I have made some adjustment. So if you are following with your set of slides, you perhaps ought to mark up your particular slide. And the change is to provide some more clarity on what the rules are. So the Eurocode says, first of all, provide horizontal tying and vertical tying. And if you can provide horizontal and vertical tying for Class 2B buildings, you have finished your responsibility. If you cannot provide horizontal and vertical tying, then you go on to consider what's called notional removal. And that is to limit the area of collapse, in this case to 15% of the floor area or 100 square meters. But remember, it's almost always easier to satisfy the first requirement, which is to provide horizontal and vertical tying. And then finally, if you cannot provide the tying and you cannot limit the area of collapse to 100 square meters, then finally you would have to design the element for 34 kilonewtons per square meter. It's described as a key element. This will be very challenging to design something for 34 kilonewtons a square meter. It is a very high load. If you think about the load on a floor, 5 kilonewtons per square meter, we are thinking about designing this elevation here on my left for 34 kilonewtons a square metre. It is a very, very large load. So practice is to say, if we did apply 34 kilonewtons per square metre to this elevation, some of this would blow off. So the cladding perhaps would blow off, the windows would blow out before that leaves just the column. I know we're in a concrete building, but let's imagine we were in a steel building. So common practice in the UK is to say, okay, well, I will design the cladding until it blows off, and then I will look at the column that remains, and maybe there will be a strip of cladding which remains. Maybe that strip of cladding is 1 metre wide, and I will design that 1 metre wide strip for 34 kilonewtons per square metre. Otherwise, it will be very, very difficult to sustain 34 kilonewtons per square metre on the whole of an elevation. A very difficult job indeed. So in terms of robustness then, it will be a key design consideration. There are some issues, because if you have designed your connection assuming it's a nominal pin, and you are assuming that not very much moment is carried into the column, if you have to make the connection stronger to resist the tying force, then maybe you need to think again about the design of the connection. And maybe that means you have to think about the design of the column, because you will be carrying more bending moment into the column, and that may damage your column design. In terms of splicers, if you choose a bearing type splice, then in compression there is no design requirement. The design requirement will be the tension force which arises due to the robustness rules.